Hello, everyone, and welcome to another episode of In Plain English. I'm your host, Jamie Moffa, and this episode marks the first in another series of interviews that I conducted at a conference, similar to the SFN Shorts series that aired in late 2023 and earlier this year. This time, I attended the conference for the United States Association for the Study of Pain, or USASP, which was a really interesting conference in that it blended both clinical research on pain in hospital settings or outpatient settings, people who have chronic pain or different kinds of pain disorders. And it also included research on the basic science behind pain. So understanding mechanisms of pain, how the brain is involved in pain, how pain is transmitted from the periphery of the body up to the brain, and a lot of other really cool research. So this is a series of interviews with people who are presenting their posters at that conference. It will cover both basic science and clinical research, and will give you an idea of what kinds of research is happening in the field of studying pain and understanding more about what causes pain and what causes chronic pain and how we deal with that clinically and from a basic science perspective. So I hope you enjoy. Our first guest for this episode was Dianise Rodriguez Garica, a graduate student at the Medical College of Wisconsin. Her research focuses on how skin cells could be involved in the pain that sickle cell disease patients feel when they experience sickle cell disease flare-ups.
So can you first start by introducing yourself?
Of course. My name is Dianise Rodriguez Garica. I'm a fourth-year graduate student at the Medical College of Wisconsin. And I study keratinocytes and how they may have a role in just sickle cell disease pain.
Okay, can you first start by telling people what keratinocytes are?
Of course. Keratinocytes are the most common epidermal cell. They actually make up about 95% of the epidermis, so that's the outermost layer of your skin. So they have a very protective effect. Of course, it's like the first barrier. They want to keep water in, microbes out. And that's exactly what we thought. That's exactly that. They were inert to sensation, but now our work and other people's works has kind of identified them as having more of an active role in sensation. So
can you tell me a little bit about what you were looking for and what?
Of course. So sickle cell disease is a very common inherited blood disorder. It actually impacts about 6.5 million people worldwide. And patients with sickle cell disease have really bad mechanical allodynia. So something as gentle as, your clothes on your skin can be very painful. And although, there's been a lot of work in looking at, the central nervous system and sensory neurons and everything like that, the mechanisms aren't fully understood. And with, skin cells being the first ones that you encounter with this type of stimulus, that's kind of the area that I was interested in pursuing. To kind of address that question, we have a really cool mouse model that has, that mutated sickle cell, which again, it's that hemoglobin that's going through your body, and it's very important for delivering oxygen, delivering, kind of keeping your body going as it should be. So we have a mouse model that really, one has those mutations that allow for the development of the patient, kind of some of the concerns that patients express, which is mechanical allodynia, as I mentioned, and then also thermal, but my context, everything is basically mechanical. So my kind of major question was, do these epidermal cells contribute to sickle cell disease pain? And, kind of two main directions that I took was, how do the keratinocytes themselves change? And then how does the keratinocyte to the sensory axon communication change? Because this is how you kind of get into how does the flow, right? How does the information get to the pain? So those were the two main questions. And I just kind of started with again, looking at just the keratinocytes itself and how they might be changing. And just long story short, what I kind of found was that these keratinocytes, isolated from the sickle cell disease mice, are more sensitive to the application of an agonist for a mechanical ion channel, which is piezo-1. So they basically kind of hinting that these keratinocytes might be more sensitive to just touch compared to their control counterparts.
Okay. So it'd take a lighter touch then to like activate.
Exactly. That's kind of the idea of like, instead of, a punch being like painful, you then a caress can become painful.
Wow. Okay.
So kind of that threshold of activation may be shifted. So that was kind of like the first direction. And, this is all good and well, but this in isolation without signaling onto the sensory axon really doesn't make a lot of sense.
Right.
So that's what I moved on next to, which is, okay, well, whatever these changes are happening here, how are they influencing how these keratinocytes are able to send information into the sensory axon and then therefore obviously up to the brain so they can process and actually feel the perceptive pain.
Yeah.
So the first thing that I did was I isolated, again, these keratinocytes from either sickle or control mice. I cultured, they are very cute. I can show you a picture if you want.
Yeah, sure.
But once I had them in culture and they had their kind of like the brick and mortar morphology, I took out their conditioned media. So it's basically just media that was either not exposed to any keratinocyte at all, either a control keratinocyte, or lastly, in the group of interest, our sickle cell keratinocytes. So it was like, okay, the idea was that we were going to capture everything that these keratinocytes release. So I took that media, injected it into the paw of just naive mouse, so just a healthy, happy mouse. And then we did evoke behavior, particularly using von Frey up-down. And what I found was that after 30 minutes of injection of these mediators, the mice that had been exposed to sickle cell disease keratinocyte media had very, very dramatic decreases in those thresholds. So they were very, very sensitive to mechanical stimuli, both at 30 minutes and 2 hours. I didn't test further, but that is crazy compared to their controls, which kind of stay the same. Obviously, there is an effect of being injected. We know that that is important. But sickle cell disease keratinocyte media definitely is playing a role in decreasing, just making these animals way, way, way more sensitive. And then from there, I kind of wanted to look into, okay, well, what cells are they mediating these effects through? And of course, there's two subjects that we are interested in, which is, of course, keratinocyte to keratinocyte communication. So that's where I started, where I took naive keratinocytes, so just, again, keratinocytes as isolated from a happy, healthy mouse. And then I exposed them to either a blank media, a control media, or a sickle cell disease keratinocyte media. And what I found, again, with exposure to that mechanical relevant channel agonist, that as you expose them with sickle keratinocyte, but not control keratinocyte media, they have way, way more responses. So they are becoming potentially more sensitive to mechanical stimuli.
And is that still in a von Frey, or
no,
what
so
is the responses?
This is all calcium imaging studies. So
this is in cells.
Exactly. So these are isolated cells that I basically use a calcium indicator if you're at 2 a.m. And you can track how these cells respond. And that's exactly what this right here kind of shows, which is you start kind of like at a baseline, and whenever I add that agonist, you can see a bump, and then a recovery, and then bump again, and recovery. So that is exactly what I was looking at. So they are basically more keratinocytes are responding to that very low dose of that piezo-1 agonist. So that's really cool, all fair, right? But this is keratinocyte.
Yes.
So my next question was like, okay, well, yeah, keratinocyte to keratinocyte communication is altered. What about keratinocyte DRG communication? Is it altered? And if so, how? So what I did was, again, isolated DRG neurons. We just...
and so those are just like the sensory neurons.
Exactly. Sorry. Yeah. So we did our dissection with, again, happy, healthy mice, and isolated those sensory neurons in culture. And again, similar setup where we expose them to a calcium indicator, which whenever there's calcium, basically this molecule emits a light, a wavelength versus non-bound to calcium. And then we expose to a mildly depolarizing stimuli. So potassium is, very well characterized as a driving not keratinocytes, DRG neurons to just respond. So that's exactly what I did. And I found that when you incubated those naive DRG neurons with either of the treatment groups, blink, control, or sickle cell disease media, they really didn't affect how often the cells responded. And again, responses looking at calcium influx.
Yeah.
However, when they did respond, how big those responses were was changing in such way that the naive neurons incubated with that sickle keratinocyte media had bigger responses compared to their control or just a blank media, which is really cool and very promising. However, for me, it was a little bit puzzling to see that there's no effect on the rate of response, but on the quality of the response. Yeah. So that was really cool. But of course, you may be asking yourself of okay, well, this is all cool and everything like that, but what is it in that media? Right. And that is something that I'm actively doing right now. I've done a couple of ELISAs, kind of trying to go for, our usual suspects. For me, I kind of started thinking, okay, well, what do we know that sensitizes these sensory neurons? Mm-hmm. I immediately thought substance P and CGRP. I ran the ELISA for CGRP, so that kind of trying to detect CGRP in these samples. I did not find anything at all.
Okay.
Which is fine, right? I think that by itself is very important, right? But something that I was very surprised by is that substance P, which again, very well, known as a having an involvement in making these sensory neurons more sensitive, was indeed very highly expressed in these samples of sickle cell disease keratinocyte media compared to their control and also a blink. So this is normalized against blink.
Gotcha.
And this was very promising to me because I was like, oh, well, that is one potential mediator inside of this kind of cocktail of we call it skin milk.
Skin? Oh,
no. So with kind of identifying one factor, which is likely not the only one, I was able to then kind of run the similar type of setup of taking naive skin cells, these keratinocytes, and then exposing them to different concentrations of substance P, similar to those that we kind of identified with our ELISA. And what I found is that, when you expose just a naive keratinocyte to different concentrations of substance P, you are able to shift how they respond to, again, this is YODA1, which is the piezo-1 agonist, which is very exciting, particularly because we know that in patients that have sickle cell disease, plasma levels of substance P are incredibly high. And this is exactly what I'm showing here. It's work from our collaborator, Amanda Brandow at the Medical College and Freighter Hospital. So that was really cool because I was like, oh.
Right, so it tracks.
Exactly. And then again, I think more very exciting to me is this is based on, or there's relation to patient data, which at the end of the day, if you do basic science, that's all good and well, but if there's no actual translation into patient and a person and how they're experiencing pain, then it doesn't really have a lot of validity. But kind of wrapping it up, kind of this work is showing us that keratinocytes in sickle cell disease, one, have increased piezo-1 activity compared to their control, so they are potentially more sensitive to mechanical stimuli. And then whatever these keratinocytes are releasing is causing mechanical hypersensitivity in just naive mice exposed to it. And then further, that the media itself, when you expose naive keratinocytes and neurons, has an effect to shift how they respond in such a way that they are now more sensitive. And then lastly, a potential candidate, and likely not the only thing in this media, is substance P. So obviously there's a lot of future directions to go, but it is very promising to see that, the microenvironment in the skin might be driving a lot of, or maybe contributing to the pain that people have in this condition and other conditions too. But that's kind of my spiel.
Thank you so much for recording this for the podcast. This was amazing.
Our second interview for this episode features Christina Mecca, a graduate student at the Medical College of Wisconsin. Her research focuses again on skin cells, but this time on their role in neuropathic pain or pain after a nerve injury. This is a very special interview as Christina was one of the winners of the Poster Presentation Awards at the USASP conference.
Hi, I'm so excited to be here. My name's Christina Mecca. I am a fifth-year grad student at the Medical College of Wisconsin, and what I study is how the skin is involved in neuropathic pain. So you just interviewed one of my colleagues on her work in keratinocytes. I'm doing a little bit of a different flavor where I am looking at the role that these keratinocytes play after traumatic nerve injury, right? Which is an interesting niche to fill because when we think about traumatic nerve injury or neuropathic pain, we think about the context of what the nerve is doing. Right. However, what we forget about is that after this injury, right, this nerve has abnormal firing and can be affecting cell types that are around it. So these keratinocytes themselves are not directly injured, however, are subjected to an environment that can alter their normal behavior, right? And so that is what I am investigating. And what we believe is that after this traumatic nerve injury, these keratinocytes that are innervated in that region become sensitized and contribute to mechanical evoked hypersensitivity, right? i.e. mechanically induced pain. And so the very first thing I did was I took these keratinocytes in culture and I used an agonist called YOTA1, which is specific to a major mechanotransducer called piezo1 in the skin. And what we saw was that these keratinocytes isolated from this injury model had increased calcium transients, i.e. were sensitized to this piezo1 agonist. Okay. The next thing we wanted to look at was using patch clamp electrophysiology. We wanted to look at, are they mechanically sensitized at this level? And what we did see was that, yes, indeed, there is a trend showing that these keratinocytes after traumatic nerve injury have a decreased threshold to mechanical force. We then wanted to know, what does this translate out to the level of the peripheral fiber? And what we found using a ex vivo teased skin nerve preparation where we looked at the tibial nerve, we saw that A delta fibers in this region had a sensitized response to mechanical stimuli. And so what we're kind of wondering, what this sets the stage for is, are keratinocytes communicating with these A delta fibers to mediate mechanical hypersensitivity?
And those A delta fibers are sensory fibers that are innervating the paw.
Yes, that is correct. And so the next thing we wanted to do is we took what the factors that these injured keratinocytes were releasing in the media, and we exposed them to naive sensory neurons in our calcium imaging, and we tested them looking with a moderately depolarizing stimulus of potassium. And what we saw was that, yes, indeed, there were factors secreted by these injured keratinocytes that were sufficient and altering calcium responses, pointing to sensitization in these naive sensory neurons. We took that a step further, and in a co-culture model with naive sensory neurons and injured keratinocytes, we looked at intrinsic excitability, and we saw that there was an increase in spontaneous activity of these sensory neurons, so they depolarized more frequently. We saw that their resting membrane potential was more depolarized. However, their spontaneous action potential firing at rest was not altered, which you may think that's a little weird, but what we're wondering is if these keratinocytes at rest are setting the stage to when a stimulus comes in, perhaps a mechanical stimulus coming in, makes it more likely, or they're more readily able to fire an action potential to a lower threshold stimulus like we've been seeing up to this point.
Right. So at baseline, they're not firing any additional action potential.
They're not firing any more than they normally would. Right. However, they are having an enhanced intrinsic excitability.
Okay.
Right? So the stage has been set. So maybe keratinocytes aren't important for spontaneous pain, but this is setting the stage to look at mechanical, right? Which is what we're interested in and the next part of this project. We then, though, however, wanted to know, this is awesome all at the cellular level. How does this translate to a living animal? So we took that conditioned media from these injured keratinocytes and we injected it into a naive mouse hindpaw, and we tested their mechanical sensitivity using the von Frey test. And what we found was absolutely shocking. Within just 1 hour post-injection of this with these keratinocyte factors, we saw that they were actually able to recapitulate the hypersensitive phenotype that we see in this injury model in naive mice. And that this lasted for about 24 hours post-injection, showing that there is indeed some type of or a host of signaling factors contained in this media, right, that keratinocytes themselves are secreting to help promote this mechanical allodynia, right?
Wow, yeah.
And so the very last that we wanted to know is, okay, so we know if we inject them with this media, they're hypersensitized. What happens if we selectively inhibit the keratinocytes themselves within this injury model? And so what we used was an archaerodopsin genetic mouse model where the keratinocytes themselves express selectively this proton pump where when we shined an amber laser on them, hydrogen ions would flow out of the cell and hyperpolarize, i.e. make them less likely to signal.
Okay.
And so when we did that, in the von Frey, dynamic brush, and noxious needle, all different forms of mechanical sensitivity testing, we found that when we inhibit these keratinocytes, we actually are able to reverse that mechanical hypersensitive phenotype, showing that it is indeed some type of signaling that is occurring at the level of the keratinocyte to drive this phenotype. It means that going forward, we can target the keratinocyte to see if we can alleviate this type of sensitivity in patients.
Right. Well, and skin cells are a lot easier to reach than
They're
neurons.
easy to access, they're cheap, and when you target the skin selectively, you remove the involvement of the nervous system, which is where most of these really harsh side effects occur, right? So you can have something that has a low abuse potential, is easily accessible to all levels of patients, right?
And you can just apply it to your skin.
And you just apply it to your skin, right? Whenever you need it. You don't need to do it every day. You can do it when you're in pain, and it's great.
Yeah. Well, that is a really amazing finding, and thank you so much for talking to me about this.
Thanks for making time. I know you're super busy, but...
Our final interview for this episode features Eric Vilsmark, a second-year medical student at the Frank Netter School of Medicine at Quinnipiac University. His research focuses on more of the clinical side of pain, researching how different risk factors or resilience factors that contribute to chronic low back pain might also contribute to patients' misuse of their opioid medications.
Yeah, can you start out by introducing yourself?
Yeah, so my name's Eric Vilsmark. I'm a second-year medical student at Frank Netter School of Medicine. And this is work we did with folks at Pain Research Lab at the Brigham. And what we were looking at was, we know that there are certain risk and resilience factors that contribute to the experience of chronic pain in people with chronic lower back pain. But we wanted to extrapolate that and see if those same things that might contribute to make that pain worse or better would also contribute to making them misuse their opioid medications more or less.
All right. So what are some of those factors, contributing factors to chronic pain?
Yep. So we had the participants do baseline surveys. So some of those things are the actual severity of the pain. We had them do a pain catastrophizing scale. That's something that asks them, how much do you kind of freak out about your pain?
Right, yeah.
How much are you thinking about it every day? Those kind of things. A general scale of how anxious or depressed you are. Something that assesses and those two things would be things that are risk factors for a worse pain experience. Then we have things that are make you more resilient. So how much you accept your pain, that's the chronic pain acceptance questionnaire. And then mindfulness was a factor in that as well. How mindful are you? How are you thinking about your pain in a mindful way? Those are resilience factors.
Gotcha.
So basically we did something where we kind of made all those variables fight it out to see which ones were over and above contributed more to either risk or resilience, how much they made so the pain go up. But then we also did it for how much it made them maybe misuse their opioid medications.
Right.
So that's to say, they might take their medications more or like differently from how they're prescribed, which some people tend to do when they're on these medications for a long period of time.
Right, yeah.
With that, we found that mindfulness over and above contributed significantly to reducing the amount that they would take their medications. So that's to say that people that scored higher on mindfulness might have been misusing their opioid medications less.
Okay.
So that's interesting.
That tracks.
Whereas people that are freaking out about their pain, which is this catastrophizing, that was over and above the other variables we put in for making them want to take their medications more.
Right.
In a different way than the doctor had asked them to. So this just kind of reflects that. It's called hierarchical linear regression. It sounds fancy, but really it's just making the variables kind of duke it out and see which ones come out on top. and those are the two we found. So that suggests that maybe when people are taking opioids over long periods of time, we should be offering them some adjunct mindfulness sessions, perhaps, or aiming to reduce the catastrophizing, how they're thinking about their pain. Because we don't want people to be taking their opioid medications unsafely.
Absolutely, yeah.
So that's it.
Yeah.
Yeah.
That's very cool, very straightforward and to the point. Well, thank you so much.
Thank you. Thanks, Jamie.
And that is all for this episode of In Plain English. Once again, our interviews for this episode featured Dianise Rodriguez Garica, Christina Mecca, and Eric Vilsmark. You can follow along with their posters at inplainenglishpod.org, where you can also find the previous episodes of this podcast and the transcripts. Our music is by Sam Brunwasser. You can find more of his work at soundcloud.com/visualsnowbeats. As always, you can download the paper and read the transcriptions at inplainenglishpod.org. And make sure to follow us on Twitter, Facebook, and Instagram at Plain English Sci. That's PLAINENGLISHSCI. Thanks again for listening, and we'll see you next time for another episode of In Plain English.